Okay, so let's get started, or let's continue our discussion. Let me scroll back up here. I think the last time we were here, we were talking about the critical point of a liquid, which, if you remember, we said that at the critical point where we're talking about the combination of the critical temperature and the critical pressure for substances, we cannot determine or make a distinction, I should say, between the liquid and the gaseous state. Let me just remind you of what we talked about here. Remember, we talked about this setup here. Go to full screen mode. We talked about this setup here, where you have a room temperature liquid, and you have the vapor above the liquid in this capsule. And then as you increase the temperature, the amount of vapor increases. And then when you get to the supercritical fluid point, as you can see here, you cannot tell the difference between the two states. And that's where you get to the critical temperature and the associated pressure at that point, right? So that's what we were talking about here. And this is just some examples of different substances and their critical temperatures and pressures. Okay, so that's where we left off the last time. So now we're going to talk about phase changes involving solids, right? So we all know what melting is. Melting is what happens when you have the transition from the solid to the liquid state. And then you have fusion, which is the reverse of that process, all right, where you're going from the liquid to the solid state. So the temperature at this point where you have that equilibrium is the melting point or the freezing point, right? The freezing point, melting point, they're both the same thing. And the enthalpy of fusion is the amount of heat required to melt a given amount of a solid. And usually it's expressed in kilojoules per mole, all right? And then we have another process, which is called sublimation. And sublimation is basically what happens when you have a solid being converted directly to the vapor state without going through the liquid state, right? I don't know how many of you are, well, you should be familiar with dry ice. Dry ice is basically frozen carbon dioxide. And if you have had an experience with dry ice, if you take a piece of dry ice and put it on a surface, you know, under normal room temperature conditions, then we all know what's going to happen. The piece of dry ice will shrink. You'll see vapors emanating from it. And that's because the dry ice is undergoing sublimation when that is happening. So that's another example. That's one example of sublimation. Another example is shown here, iodine, which exists normally as solid. If you heat it slightly, or even if you leave it open to the atmosphere, what happens is that the solid iodine will be converted to the iodine vapor. So that's another example of sublimation, all right? So those are the two types of changes that, in terms of phase changes, that solids tend to undergo. They either undergo melting or sublimation, all right? And what you'll find is that there is a quantitative relationship between the enthalpy of sublimation, the enthalpy of fusion, and the enthalpy of vaporization. And that's the equation right here. Enthalpy of sublimation is equal to the enthalpy of fusion plus the enthalpy of vaporization. And we can actually show this to be true based on Hess's law. Let me show you how that is done. Let me get rid of it. So I'm going to use iodine as an example. So if we're looking at iodine solid going to liquid, that is called delta H fusion, all right? And then going from iodine in a liquid state to iodine in a gaseous state, this is delta H vaporization, enthalpy of vaporization. If you were to add these two together, this will cancel out with this, so you'll be left with iodine solid to form iodine gas. And the enthalpy of that would be enthalpy of sublimation, which, as we know, if you use Hess's law, which means that you have to add these two to get this, so that would be equal to enthalpy of fusion plus enthalpy of vaporization. So this is basically just me showing you why this equation is true based on Hess's law as applied to applied to these three reactions, all right? Or not reactions, but changes of state. Okay, so let me go back to this here. And this table here is basically giving you some examples of different substances and their corresponding enthalpies of fusions and melting points, all right? And as I said before, the unit for the enthalpy of fusion is usually expressed in kilojoules per mole. Okay, so next thing I want to talk about here is a relatively simple concept of heating and cooling curves. And basically what this shows you is how the temperature changes with time as you're heating a substance from its solid state to above, all right? So this could apply to a wide variety of substances as long as they don't react while you're heating it. So we could use H2O as an example. As we all know, H2O exists in 3 states like most other substances. Below the freezing point, it exists as a solid. So let's say that we have below the freezing point here, which is actually, this is actually showing you what happens in the case of H2O. So if you're heating it, it warms up, the temperature increases as time progresses until you get to the melting point. So when, of course, you get to the melting point, what you start seeing or observing is the conversion of the solid to the liquid, right? Now, what you need to remember and keep in mind is that as this conversion is taking place, the temperature remains the same, right? So you'll notice that there's a plateau here in the cooling curve, right? Where you have the coexistence of the solid and the liquid state, right? So as long as you have solid present, the temperature will remain at the freezing point, and that will continue until all the solid is converted to the liquid. So once you have only liquid at this point, and you're still adding heat to the system, then of course what will happen is that the temperature will increase, all right? And that will just basically continue until you get to the boiling point. Now, unfortunately, that's not shown here, but I think I can show you what's going to happen after that. So let's say that here, I'm just going to do a dotted line right here, all right? So let's say that here is a freezing point, I'm sorry, the boiling point, which for water is 100 degrees Celsius, all right? So basically what happens at the boiling point, of course, is that you're going to have a conversion of the gas, of the liquid to the gaseous state. So basically what will happen is that you're going to have a flat line again. And at this point, you're going to have both the gaseous state and the liquid state existing, coexisting, right? So as long as you have liquid at this point, the boiling point will remain, the temperature will remain at the boiling point until all the liquid is converted to gas, and then you're going to have the temperature rising again. And of course, at this point, the only substance you'll have will be the gaseous state, all right? So that's basically what happens. Of course, the values of the boiling points and the freezing points will differ according to the substances, and even the length of time required for melting or vaporization will vary as well for different substances, all right? And that's basically what happens when it comes to the heating curve. And the cooling curve is basically the flip side or the mirror image of the heating curve, right? So if you understand what happens as you're increasing the temperature, it's a reverse that will happen when you're decreasing the temperature, and the changes will take place as far as the different states and the temperature at which those changing states occur, all right? Okay, and that's basically all I have to say concerning heating and cooling curves. So the next thing I want to talk about now is something that we were introduced to briefly earlier, but we're going to go into more detail, all right? So what you're looking at here is what we call a phase diagram. And the phase diagram basically is a graph where you have the plot of pressure on the y-axis and the temperature would be plotted on the x-axis. And you have the curves which represent the different lines here, which represents the different temperature and pressure where you have different states coexisting at equilibrium, all right? So the first line we're going to talk about here is the fusion curve, which is going from A to D right here. And what this line represents are the various pressures and temperatures where you have an equilibrium between the solid state and the liquid state, right? So basically you can tell based on this line here, if you had the scale for the temperature and the pressure here, you can tell basically at what pressures and temperatures you will have the melting points or the equilibrium between the substances. So the temperatures at this point along this line here would represent the melting points for various pressures, right? So we call that the fusion curve, okay? And then the sublimation curve, which is this line here, represents the pressure and temperatures where you have an equilibrium between the solid state and the gaseous state here, all right? And then the third curve from A to C basically shows you the various pressure and temperatures where you have an equilibrium between the gaseous state and the liquid state. So we call that the vapor pressure curve, right? So that's basically what each of these lines represent. Now, for these regions here, here, and here, basically these regions are where you'll find one particular state at the indicated temperature and pressure, right? So if you have, let's say you want to look at a temperature at this point right here. And let's say over here, you have a pressure here. Well, basically, So basically, at this pressure and this temperature here, that substance will basically exist as a liquid, all right, under those conditions of pressure and temperature, all right? On the other hand, just to use another example, let's say we're looking at this temperature and this pressure. So basically, you draw a line like this and another line like that. Again, they will intersect here. So therefore, at this pressure, and this temperature, the substance will exist in a solid state, right? Now, if you look at a point like here, right, on this curve right here from A to C, right, that means that the corresponding pressure would be here, right? And the corresponding temperature here would be the boiling point at that pressure, all right? So that's basically how we use the phase diagram for different substances. We can tell whether or not a substance will exist in a particular state by itself, or we can tell whether or not it will exist, a substance will exist as two coexisting states based on their location on this line, or I should say based on what their pressure and temperature would be correspondingly, all right? So that's the phase diagram. All right, of course, for different substances, the phase diagrams will have different appearances, and in some cases, look not as neat as this. But before we leave this here, remember we talked about the critical point. The critical point in this particular phase diagram is right here, all right? So that means that the critical temperature will be down here. That's a critical temperature TC, and the critical pressure would be here, TP, all right? Or PC, I'm sorry. Okay, and remember what we said about the critical point? Basically at that temperature and beyond, and that pressure and beyond, you cannot identify a distinction or detect a distinction between the gaseous state and the liquid state. Okay. All right, so as I said before, there are some substances that give some weird looking phase diagrams, such as this phase diagram here for mercury 2 iodide. And as you can see here, what makes this weird is because in the case of mercury 2 iodide, in the solid state, it can exist in two forms. You have the alpha form here and the beta form here. So therefore, that has to be taken into account when you're constructing the phase diagram for such a substance. So basically, you have two solid states, basically, for lack of a better way of expressing it. And then you have the liquid state, and then you have the gaseous state over here. You have the supercritical fluid in this region right here. So basically at 1 atmosphere, for example, where the pressure is, of course, the regular atmospheric pressure, the melting point, or I should say the the boiling point is 354 degrees Celsius. The melting point of the mercury iodide is 259 degrees Celsius. And here we have, this would not be a melting point per se, because what this temperature here represents, the 127 degrees, that's a temperature where you have the equilibrium between these two different forms of mercury, right? So I'm not sure what the terminology is that would be applied to this temperature, but it certainly would not be the melting point, because we're not talking about going from a solid state to a liquid state. We're going from one form of solid to another form of solid. So that's what happens in the case of mercury to iodide. Okay, let me see here. And then you have a triple point here where you have an equilibrium between the two forms of mercury iodide and the gaseous state. And then you have another triple point here where you have an equilibrium between this form of mercury iodide, the liquid state, and the gaseous state. So as you can see, this is more complicated than the diagram that I showed you before. And that's complicated because, as I said before, we have these two different forms of mercury 2 iodide that is taken into account when constructing this phase diagram. Okay, let me continue. Okay, so this is the carbon dioxide phase diagram, right? And 3 different states. Remember, we talked about dry ice. Dry ice is basically frozen carbon dioxide under 1 atmosphere temperature. Sublimation will take place, I should say 1 atmosphere pressure. Sublimation will take place at minus 78.5 degrees Celsius, all right? So, you know, no surprise there, because of course we know that dry ice will basically sublime at even room temperature. That's what happens. So this is, of course, the line representing the equilibrium between the solid state and the gaseous state. So carbon dioxide will sublime from basically along this line up to and including minus 56.7 degrees Celsius, all right? In terms of the equilibrium between the liquid and gaseous state, that's represented by this line here. So from minus 56.7 degrees to 31 degrees Celsius, you'll have the conversion of liquid carbon dioxide to gaseous carbon dioxide. Now for that to happen, of course, the pressure would have to be between 5.1 atmosphere and 72.9 atmosphere. So these are not regular room temperature conditions where you'll have that transition between the liquid state and the gaseous state, all right? And then between the solid state and the gaseous state, basically that temperature would be minus 56.7 degrees Celsius, all right? So, and then it curves, so it goes up. As the pressure increases, the temperature at the equilibrium temperature will increase slightly, all right? So not as complicated as the mercury 2 iodide one, but it's a bit weird still compared to the first one that we looked at. Okay, so this is the phase diagram for water, and water is a bit different because of this part right here, right? Most other substances, this particular curve would be leaning to the right, but in the case of water, it leans to the left. And it says here, the reason for that is that as the pressure increases going up here, the melting point, as indicated by what happens on the x-axis, decreases, all right? And there's a reason for that. It has to do with some changes that takes place within the substance at the microscopic level, which I won't get into right now. But this is basically the phase diagram for water. So based on this, you can determine the boiling points of water, for example, at different pressures. So at 1 atmosphere of pressure, the boiling point of water, of course, is 100 degrees Celsius. Same thing is true for the freezing point. At 1 atmosphere pressure, the freezing point is 0 degrees Celsius, all right? And of course, you can also have sublimation between the solid state going to the gaseous state, but of course, that would mean that the pressures would be lower, especially lower than 1 atmosphere, and the temperatures, of course, would be lower. So basically, in this region here is where you have sublimation taking place, where you have the equilibrium between the solid state and the gaseous state, all right? So The regions, of course, represent actual states or phases by themselves. Even though it's not labeled here, let me just write the labels here. So this would be, well, actually it's labeled here. This would be the solid state. This region here would be the liquid state. And this region here would be the gaseous state. So those are the three states, regions in the phase diagram for water. Okay, so that's basically it as far as phase diagrams are concerned. Now, what we'll be looking at in this section are the different types of intermolecular forces that exist within substances, all right? And we're going to explain how the structures of molecules especially relates to the intermolecular forces that exist. So the first type of intermolecular force we'll be looking at are known as dispersion forces. And these are forces that exist in substances which are made up of nonpolar molecules. So let me put nonpolar molecules. All right. So when it comes to nonpolar molecules, remember nonpolar molecules have no separation of charge. And I can just simply use a diagram like this, which represents a nonpolar molecule. It's perfectly uniformly distributed in terms of the electrons involved, and therefore there are no charges present. Now, even though there are no charges present, what you'll find is that nonpolar molecules in these compounds will be attracted to each other in any case. So this begs the question, why is it that there is some attractive forces between these nonpolar molecules? Well, that's where dispersion forces comes in. And as stated here, dispersion forces are forces of attraction that occurs between an instantaneous dipole and an induced dipole. Now, let me explain what's happening here. As I said before, a nonpolar molecule has no dipole present. But what you'll find is that because the electrons are always moving, right? Electrons are always moving because they're high energy within the molecule. What you'll find is that at one instant, you'll have what is called an instantaneous dipole being formed, right? So for a millisecond, or maybe even a microsecond, you'll have a temporary dipole present within the molecule, right? So you'll have the displacement of the electrons to one side of the molecule such that one end is partially negative and the other end is partially positive, right? When that happens, then that will induce a dipole in another molecule that's next to it, all right? So basically, once you have an instantaneous dipole formed on one molecule, then that would basically cause another instantaneous dipole be formed on an adjacent molecule. So let's say that this is the molecule which initially has the instantaneous dipole, right? You have the negative end here and the positive end. This positive end is going to attract the electrons from the other molecule to the negative end here, and therefore this will become positive. And that continues throughout the whole substance, right? And therefore, as a result, you have an instantaneous force that exists between these two induced dipoles, all right? So that's basically what we mean by dispersion forces. Dispersion forces are the attraction that exists between a dipole that is formed instantaneously and one that is induced on the next molecule to it, all right? Now it turns out, so as a result of that, there will be an attractive force between these molecules. And therefore, as a result, these molecules will be held together, especially in a liquid state, if the temperature is low enough, all right? Now it turns out that the tendency for an instantaneous dipole to be formed is a function of a couple of things, not the least of which is what we call the polarizability of an atom. That's a very long word for me to handle. But basically what this is suggesting is that the more polarizable the molecule is, the more easily it is to be instantaneous, for an instantaneous dipole to be formed, and therefore the more easy it is to induce dipoles in adjacent molecules, all right? And the ability of a molecule to be polarized is dependent itself on other factors, including the size of the atom or the size of the molecule, all right? So the larger the molecule, the more easily it is to be polarized, all right? And that explains certain observations. Now, this is not the one I was thinking of, but if you look at the halogens, in fact, let me go to my writing pad here. So if you look at the halogens, you'll find that in terms of boiling points. So let me say boiling points, right, of halogens, right? I'm going to use X to represent halogens, right? What you'll find is that fluorine is the lowest in terms of boiling point compared to chlorine, compared to bromine, and then the next is iodine, all right? Now, the reason why that is so is because, well, firstly, all these molecules are nonpolar, right? All these molecules are nonpolar, right? So therefore, what you'll find is that in terms of the type of forces that exist between them, what you'll find is that the intermolecular forces in this one would be greater in the case of iodine. And the reason why, so greater intermolecular forces or greater London forces. Oh, by the way, I've neglected to mention this. Let me go back to the PowerPoint here. Right, the dispersion forces is the same thing as London forces, right? Named after Fritz London, all right? Just thought I should mention that since I inadvertently mentioned London. So let me go back to this here. So in the case of iodine, it has in this series the greatest in terms of London forces existing within it, right? And the reason why is because the iodine molecule is larger and therefore very polarizable. All right? So that's what happens in the case of iodine. On the other end of the spectrum here, smaller London forces will exist. London forces, right? And that's because F2 is smaller and not as polarizable. Polarizable, all right? So that's the reason why iodine has a greater, or of these elements in group 7, iodine here has a greater boiling point because the intermolecular forces, the London forces will be greater, and that's because iodine is larger and the molecule is more polarizable, right? And the opposite is true in the case of fluorine. So that explains that. Now, going back to the PowerPoint slide here, the example that, is used of organic molecules. Now here we have two organic compounds, octane and isooctane. If you look at these two, they have the same molecular formula, the same carbon and hydrogen count. But the difference between them is how they're structured. In the case of octane, you'll notice that it's just simply a chain of carbon atoms and the carbons are bonded to each other and to hydrogens. In the case of isooctane, you have, in this case, let me see here, you have 5 carbons in one chain and you have other carbons branching off, 2 other carbons, actually 3 other carbons branching off from that chain, right? So what you'll find is that when you compare the boiling points between these two, what you'll find is that octane has a higher boiling point compared to isooctane, right? And we can explain that to some extent using the dispersion forces or London forces idea. In that, in the case of isooctane, what you'll find is that because the chain is longer, the molecules are not as, well, the molecule will be more polarizable compared to in the case of isooctane, right? So as a result, and another thing I should mention too, which is not directly related to polarizability, is the fact that because the chain is branched, the molecules, when they assemble, will not be ready, how should I put this? Will not be, it's not a compact situation. The branching basically provides more spacing between the different molecules. As a result, the London forces in the case of isooctane are not as great compared to the London forces in the case of octane. So therefore, as a result, the boiling point of isooctane is lower compared to the boiling point of octane. So I'm not sure if I explained that clearly, but basically it has to do with the fact that the branching that exists in isooctane does not allow for the molecules to be closer to each other. And therefore the London forces in the case of isooctane is weaker compared to the London forces in the case of octane, which is basically a chain. So if you imagine several chains of this type, they'll be on average closer to each other, and therefore the London forces would be greater, all right? But the general trend is that the greater the polarizability of the molecules, the stronger would be the intermolecular forces between them, and therefore their boiling points would be greater. Okay, any questions about the London forces, dispersion forces, etc.? Any questions? Any questions?
No, I don't believe so.
Okay, so let's move on to dipole-dipole forces, which are another form of intermolecular forces. So in the case of dipole-dipole forces, which is different from the London forces that we're talking about, the dipoles that exist are permanent, right? So we're talking about polar molecules, right? So basically what will happen is that they will align themselves such that you have the positive end of one molecule attracted to the negative end of another molecule. So that's basically the dipole-dipole forces that exist between permanent dipoles, all right? And because these dipoles are permanent, let me see what it's saying. Oh, this is talking about something different, but before I get to that, okay. So because these forces, these dipoles are permanent, these forces basically are stronger, right? So what you'd find is that the forces that exist between polar molecules will be stronger compared to the forces that exist between nonpolar molecules. Another thing I want to mention here before I talk about what's over here is that even though we have dipole-dipole forces that exist between permanent dipoles, we still also have van der Waals forces that exist, I'm sorry, not van der Waals, I'm sorry, London forces that exist between these molecules. So when it comes to permanent dipoles, right, or molecules that have permanent dipoles, there are two forces that exist. You have the London forces, which are weaker, right, and then you have the dipole-dipole forces, which are stronger, all right? So that's the main reason why, for example, you'll find that polar molecules will have higher boiling points, right? Because not only do you have the dipole-dipole forces, which are stronger, but you also still have the van der Waals forces that exist in these substances. Okay, now dealing with this short statement right here, it says here that a permanent dipole in one molecule can induce a dipole in a neighboring molecule, giving rise to dipole-induced dipole forces. So what they're talking about here, let me go back to my writing pad here. So what we're saying here, let's say you have a molecule, right, where you have a permanent dipole, right? And let's say you have another molecule here, which is not polar, right? Well, what will happen when these two are close to each other is that the negative end of this dipole will basically shift the electrons to one end of the molecule, which is nonpolar, and therefore induce a dipole. So therefore, what will happen? So this would be electron shift to one end. So the result would be, now remember, this is permanent dipole, all right? So the result would be this. Right, so this is still permanent, but this is now induced, all right? So basically you're going to have some force existing between these two, holding it together as a result. So that's basically what we're talking about here, where you can have a permanent dipole inducing a dipole in a molecule which is not polar, all right? Okay, so much for that. I alluded to some of the physical properties that can arise based on what we have discussed. One of them is a boiling point, another is a melting point, and that's what we're talking about here. Dispersion forces or London forces, which are always present regardless of whether or not the molecule is polar, become stronger with increasing molar mass and elongation of molecules. We saw that in the alkanes, in the organic compounds that we were looking at a couple of slides ago. In comparing nonpolar substances, molar mass and molecular shape are basically the influencing factors that determine whether or not the strength of the London forces, all right? Dipole-dipole and dipole-induced dipole forces are also found in polar substances. The more polar the substance, the greater you'd expect the intermolecular forces to be, all right? So based on all of this here, we can make certain predictions about trends in physical properties based on what we have talked about. In the case of nonpolar substances, molar mass and molecular shapes would be the essential influencing factors. In the case of polar substances, basically we look at the dipole moment or the polarity of the molecule, again, to determine or make predictions about trends in the physical properties of these substances. Now there's one particular type of intermolecular force, which is polar in nature, that is unusually strong. And this is known as the hydrogen bond, which, to be perfectly honest, is a bit of a misnomer because it's not a bond in the sense of being a covalent bond. It's not a covalent bond or ionic bond. It's an intermolecular force, but it is an unusually strong intermolecular force which deserves its own category. So that's why we're talking about it now. So what's a hydrogen bond? A hydrogen bond is an intermolecular force where you have hydrogen covalently bonded to an electronegative atom, right? And I should say that the electronegative atom is either fluorine, oxygen, or nitrogen, right? These are the three atoms which the hydrogen atom has to be bonded to in order for this phenomena of hydrogen bonding to be observed, right? So as I was saying here, the hydrogen atom is covalently bonded to a non-metallic atom, which would be one of the three I mentioned earlier, in one molecule, and is simultaneously attracted to a non-metal atom of a neighboring molecule, all right? So the example that is shown here is, so it's mentioned here, what I just mentioned, the three atoms must be nitrogen and oxygen and fluorine. And the reason why you're gonna see shortly why these are the three elements we're talking about in this context is because these atoms here are the three most electronegative elements in the periodic table, all right? Now, the example that is shown here is the example of water, all right? So let's focus on one water molecule here, where you have the oxygen bonded to two hydrogen atoms. Of course, the shape is bent. And then what will happen is that this hydrogen, for example, will be strongly attracted to the oxygen of another molecule of water. Now, the reason why that attraction is very strong is because of the electronegativity of the oxygen atom being very high. Because oxygen is very electronegative, it's going to have an attraction. In fact, let me go to this diagram so I can explain it more fully. Okay, so here's the oxygen bonded to two hydrogens, right? So, as I said before, oxygen is electronegative, so it's going to have a very strong attraction for the electrons it shares with the hydrogen, right? So therefore, this oxygen will be partially negative, and this hydrogen will be partially positive. Now, the key thing you need to remember is this. This hydrogen has only one electron that is being pulled away from it by this oxygen. So therefore, this hydrogen is almost a bare proton, right? So therefore, it is very, how should I put this? It has a high charge density, right? Charge density. So therefore, this will be attracted very strongly to an oxygen from another water molecule, which is partially negative. So that strong attraction is what we call the hydrogen bond. All right? So that's the reason why the hydrogen bond has its own category in terms of dipole-dipole attraction, because that force of attraction is stronger than all other type of dipole-dipole interaction. And the reason for that has to do with what I just described, the fact that the hydrogen here, with its own electron being pulled away from it by the oxygen, which is electronegative, is almost a bare proton, has a very high charge density, and therefore will have a high, a strong attraction between itself and the oxygen from another molecule, all right? So that's basically hydrogen bonding, which is a very important phenomenon because it has, it imparts a lot of properties to different substances. This explains, for example, why water has such a high boiling point and a high melting point. In fact, you know, if hydrogen bonding did not exist, then the boiling point of water would be very low, and therefore it would not exist in a liquid state under normal room temperature conditions, right? And therefore, we would not have rivers, we would not have seas, there would be no rain falling, because basically as soon as it forms, it would vaporize, all right? So it is the hydrogen bonding, believe it or not, that is responsible for water having the properties of a relatively high boiling point under normal room temperature conditions. Okay, so that's hydrogen bonding. Hydrogen bonding also, again, applied to water, causes water in the form of ice to have a more open structure. And that explains why ice has a slightly lower density than water. And it also explains why, if you look at the ice structure more closely, you'll see that it forms crystals, because the hydrogen bonding also leads to an ordered arrangement of water molecules in the solid state. Hydrogen bonding also is important when it comes to the DNA molecule, which I think is later on, right, actually right here, right? The structure of proteins and the DNA molecules and so on are actually held together by what we call intramolecular hydrogen bonding, meaning basically that you have hydrogen bonding between different parts of the molecule within the same molecule, right? So this is a DNA structure here. And as you can see here, you have a hydrogen bond here, hydrogen bond here, hydrogen bond here, between oxygen and hydrogen in different parts of the molecule, right? And this basically holds the helix, the alpha helix structure together when it comes to the proteins and so on. Okay, so I mentioned already that solid water is less dense compared to liquid. I mentioned that already. And I mentioned also the high boiling point of water due to hydrogen bonding. So let me move on to the next slide. Oh, another thing that hydrogen bonding causes is that it allows some molecules to form what we call dimers. Now, dimers basically means that two molecules come together to form one unit, right? Now, the example that is shown here is the example of acetic acid. Now, there's some experiments that if you were to determine the molar mass of acetic acid, you'll find that the molar mass, based on the experimental data, would be twice of what it should be. And the reason why is because when the experiment is conducted, it is conducted on a molecule that have this arrangement here. Now, let me explain what's happening here. You have one acetic acid molecule, which is right here. And you have another acetic acid molecule, which is right here. But what happens is that you have hydrogen bonding between this hydrogen from this molecule and this oxygen here, and the same thing happens here and here. So this would be the hydrogen bond here, and this would be the hydrogen bond here. So basically some experiment conducted on this to determine the molar mass would basically read this as one unit, where it is not. It's actually two molecules that are linked to each other by hydrogen bonding. And some data is given here about the bond lengths, just to give you an idea as to how strong the hydrogen bonding is. The covalent bond between oxygen and hydrogen here is 100 picometers, while the hydrogen bond length here is 160 picometers, all right? So basically, the hydrogen bonding is a relatively strong intermolecular force. not as strong as the covalent bond, and that's the reason why the covalent bond is shorter, but it is strong enough nevertheless, so that you can have substantial interaction between different molecules to form one unit or detected as one unit experimentally. Okay, so much for that. Oh, here's another example of an intramolecular bonding. In the case of this compound is called p-hydroxy benzoic acid. It's a precursor to aspirin. We can actually convert this to aspirin. In fact, some native people of somewhere in South America, I forgot which region, back in the day, they used to, this compound, let me just explain. This compound is known commonly as salicylic acid. And this can be found in a plant, a tree known as the wintergreen something, I don't remember exactly. Anyway, the native people of this particular area, they would basically cut off the bark of the tree and suck on it to get the pain relieving effects of the salicylic acid. Problem with that is that because it's so acidic, it can do a serious number in terms of damage on your alimentary canal, especially your esophagus, right? So a scientist, a chemist, I don't remember the name of this person, he did a reaction where he basically converted salicylic acid into aspirin, reducing the acidity, and therefore that's why aspirin is now used as a common analgesic, all right? So that's just some background history behind this compound, all right? But the point here that we're making in terms of the intramolecular bonding that exists is that you can have that in compounds such as this, where the hydrogen here is close enough to the oxygen so that you can have this intermolecular force between those two, all right? So that's another example of hydrogen bonding. Okay, another consequence of hydrogen bonding, especially when it comes to water, is this phenomenon known as surface tension. And surface tension is defined as the amount of work required to extend a liquid surface and is usually expressed in joules per meter squared, right? And we can understand surface tension if you look at things at a microscopic level, as is shown in this diagram here. So if you compare what happens, okay, so here we have water. At the surface of water, you have the water molecules at the surface being attracted to the water molecules below the surface, right? So that's what happens here. So therefore, there'll be a net force on the water molecule. If you focus on one water molecule, there'll be a net force of the water on the water molecule into the internal regions of the substance. On the other hand, if you go into the internal region of the substance, the forces that would be on one water molecule, the attractive forces, hydrogen bonding, etc., will be basically canceling out each other, right? So the result of that is that you have at the surface what we call a relatively high surface tension for the water molecule. One of the manifestations of that is that the water surface will have a sort of skin-like property, which allows for insects, like as you can see here in this picture, they're able to basically skate on the water surface because it has a kind of skin-like property on the surface of the water. Now, the type of forces that exist that I just described are two types. One is called the adhesive forces, which would be the intermolecular forces that would be between unlike molecules. So that is different from what we're talking about here. And then you have the cohesive forces, which is what we're talking about here, which are the forces that exist between molecules that are identical, all right? So the intermolecular forces that exist between the water molecules, the hydrogen bonding, as well as the other forces, because you still also have London forces between water molecules. Those forces are called cohesive forces. And this will lead us into a discussion of another observation, and that is the formation of a meniscus at the surface of a water, and also capillary action. But let me talk about the meniscus formation first. So the meniscus, by definition, is the interface between a liquid and the air above it. Now, if you're if you have been in a lab and you have measured, for example, the volume of water in a measuring cylinder, you should know that at the surface of the water, you have a lens-like appearance up here, which is a meniscus, right? And you remember, or you would know that that meniscus is curved more like a U-shape, right? Now, if you were to observe the same thing in mercury, which is a liquid metal, you see that the shape of the meniscus is not U-shaped, it's the opposite, right? The reason why you have the U-shape like this in the case of water is because the cohesive forces that exist, hold on, let me see here. Right, the cohesive forces that exist in the water substance is greater compared to, oh, I'm misspeaking, okay, let me get my bearings straight. The adhesive forces between the water molecules and the surface here, the glass surface here, is greater than the cohesive forces that exist within the water molecule, all right? Or within the water below the surface. So basically what will happen is that there's going to be a stronger attraction for the water molecules for the glass surface. And therefore, as a result, there'll be a pulling up of the water along the surface here. And as a result, you have a U-shaped meniscus at the surface of the water, right? So the adhesive forces here will be greater than the cohesive forces below the surface, and therefore the U-shaped meniscus will be the result. The opposite will be true in the case of mercury, where the adhesive forces between the mercury and the glass surface would be less compared to the cohesive forces. And therefore, as a result, the mercury atoms will be pulled closer to below the surface of the mercury. And as a result, this would be the shape of the meniscus in that case, all right? So that's basically another phenomenon that can be explained based on the type of forces that exist in a substance. And related to that, we can explain capillary action, right? Capillary action is what happens when you have a very narrow tube placed in a liquid, and the liquid just simply moves up the tube without, against gravity, without you sucking up the liquid into the tube, all right? And the reason why that happened again is because of the stronger adhesive forces compared to the cohesive forces, right? The greater attraction between the water and the glass surface results in the water molecules being pulled up into the capillary, and therefore that's what happens, all right? So we can understand these different phenomena if you just keep in mind the different types of forces that exist within a substance, the different types of intermolecular forces. Okay, any questions about any of these surface phenomena or phenomena?
No, I don't think so.
Okay, here's another property that is observed based on intermolecular forces. Viscosity, which is basically a measure of a liquid's resistance to flow. So basically, the more viscous the liquid is, the more likely that the resistance to flow would be observed for such liquids, right? So liquids that flow easily are said to be mobile, and we can actually quantify viscosity. The units for viscosity is the Poise unit, and typically viscosities are measured in centipoise. We won't do any calculations involving this, but you need to understand why some liquids are more viscous than others. Again, it has to do with the type of intermolecular forces that exist. Simply put, the stronger the intermolecular forces between the liquids, between the molecules in a liquid, I should say, the greater would be the viscosity of the liquid. And that's pretty much all we can say concerning that. All right. Let me see here. So let's talk about the characteristics of crystalline solids as it relates to the different types of intermolecular forces. So here we have a table where we have the different types of molecules, or if it's an ionic or metallic compound or element, whatever, and the type of particles, the type of intermolecular forces, and the typical properties that will be expressed based on the intermolecular forces, and some examples right here. So let's deal with one extreme of the spectrum where the molecules or atoms are nonpolar. We know what that means already. There's no separation of charge. And the only type of intermolecular forces that will exist, we talked about this earlier, would be the dispersion forces, right? As a result of that, these compounds tend to have properties where the boiling points and the melting points, well, since we're dealing with solids, let's talk about melting points. So the melting points are extremely low, right? In fact, in a large number of these cases, these substances exist either as a liquid state or in the gaseous state. And some examples are shown here, all right? So that's what happens in the case of nonpolar molecules. Now, in the case of polar molecules, the dispersion forces would still exist, but you also have dipole-dipole and dipole-induced dipole attractions. And in these cases, the melting points would be, on average, higher compared to nonpolar molecules, but they're still low to some extent, to moderate. In terms of solubility, and I should have mentioned this in the case of nonpolar substances. Nonpolar substances tend to be soluble in nonpolar solvents, all right? But in the case of polar substances, they tend to be soluble in some polar and in some nonpolar solvents. So what you'll find is that there's an increase in solubility of polar substances when it comes to polar solvents, all right? Some examples are shown here of polar substances. And then we get to, of course, the special type of polar substances which will exhibit hydrogen bonding. As we said before, the structural feature that these molecules will have is where you have hydrogen bonded to either nitrogen, oxygen, or fluorine. So the type of intermolecular forces that, the main type of intermolecular forces that will be displayed would be hydrogen bonding, right? And these compounds tend to have low to moderate melting points, and they are soluble in some hydrogen bonding and some polar compounds. And these are some examples. And you'll see, of course, in each of these cases, you have hydrogen bonded to either oxygen, nitrogen, or fluorine. Okay, so the next category of compounds or elements would be network covalent compounds. Now, I don't think we've ever discussed these types of compounds before, but basically, simply put, these are substances where if you look at their atoms and if you look at the structure, you see that the atoms are connected to each other by covalent bonds. But the thing about it is that they don't exist as discrete units, as molecules. Basically, you have a continuous linkage, seemingly forever, where you have atoms linked to each other, right? And we see that in some examples. For example, in the case of carbon, in the case of silicon carbide, silicon dioxide, and boron nitride, in these cases, you have that sort of situation. Now, the thing about it is that collectively, these covalent bonds basically would be very strong, right? And as a result, it imparts certain properties to these compounds. These compounds, they tend to have high melting points, and they tend to be not very good conductors of electricity because the electrons are localized within the covalent bonds. They tend to be very hard, all right? That's why diamond, for example, is the hardest known substance, hardest element. So therefore it's used to cut glass and so on. I think silicon carbide is actually harder, and I think it's used for the same purpose, all right? So those are the properties that would exist for compounds of this, substances of this nature, which are described as network covalent. And then we have ionic. Of course, we know what ionic compounds are. They're made up of cations and anions. Of course, the attraction between the ions are electrostatic in nature. As a result, these forces, these attractions are very strong. And therefore, what you'll find is that ionic compounds are hard, brittle, have moderate to high melting points. They are conductors of electricity in the liquid state, but not in a solid state. And most of them are soluble in water. And some examples are given here. And then finally, we have the metallic compounds. Basically, they're made up of positive ions in a sea of electrons that are delocalized. The attractive force between the ions and the electrons are said to be metallic. And again, these have properties in relation to the structure. They tend to be hard. In some cases, soft. And the more reactive ones tend to be soft, like sodium, potassium, lithium. But the higher the atomic mass, the harder they become. So iron and titanium and all these other metallic elements, they tend to be hard and tend to have a high melting points. They're lustrous, ductile, malleable, and they tend to be very good conductors of heat and electricity. All right, so some examples are given here. So this is basically a summary of the different types of properties displayed by different substances and how they relate to the structure and the type of intermolecular forces that exist within these substances. All right, okay. So let me talk about the network covalent compounds. I tried to describe it earlier, but this diagram here shows you what happens when we look at the structure of diamond, right? So basically, as you can see, it's a collection of atoms, carbon atoms, bonded to each other, all right? And if you look at it closely, if you look at, for example, this carbon atom here, you'll see that it's a tetrahedral arrangement of the other carbon atoms around it. And the same is true for each and every single carbon atom within the structure. And this just goes on and on and on. And as a result, it adopts a crystalline structure because of the ordering of the atoms in this arrangement, all right? Now, this is one form of carbon, right? Which is diamond. There's another form of carbon known as graphite, right? And the structure of graphite, let me see if I have it here. Okay, so this is the structure of graphite here, right? As you can see, the arrangement is different compared to diamond, all right? So if you look at the structure of graphite, you see that it consists of sheets, right? Each sheet is made up of several hexagons of carbons, which are fused at at different edges, right? So for example, you have 1, 2, 3, 4, 5, 6 carbon atoms here in this hexagon arrangement. And then you have 1, 2, 3, 4, 5, 6 carbons here in this hexagon arrangement. And that continues on and on for the different sheets, right? Now, you'll notice that the geometry around each carbon here is different compared to the geometry around each carbon in the case of diamond. In the case of diamond, the geometry is tetrahedral. In the case of graphite, the arrangement is trigonal planar, right? What that means is that in the case of graphite, each carbon will have an electron in a p orbital, which is not affected by hybridization. And what happens as a result of that is that you have the p orbitals for each of the carbon atoms in each of these sheets will overlap with each other to form a delocalized pi system. So what you're going to have in the case of graphite, between each of the sheets are delocalized pi electrons, which means that these electrons are mobile, and therefore that imparts a very unique property to graphite. The property that it imparts to graphite is that graphite is able to conduct electricity, right? In order for electricity to be conducted, as we learned earlier, we need mobile charges. And in this case, the mobile charges will be the delocalized electrons. So therefore, carbon, or I should say graphite, is the only non-metal that is able to conduct electricity for that reason, all right? So these two different forms of carbon, they're known as allotropes, right? Allotropes, let me go back to the previous slide, that's where the definition is. Allotropes are two or more elements of, two or more forms of an element that differ in their basic molecular structure, all right? So in the case of carbon, we have these two forms, and in fact, there are more forms actually. There's another form which is called Buckminster fullerene, which I'll probably post some information about that. And there are some other forms as well, but these are the two more common forms of, or two more common allotropes of carbon that are known, all right? Okay, let me go back to here. I think I'm missing something. Oh, so they're just mentioning here that sulfur is another element that can exist as allotropes, all right? We won't get into that though. Okay, I'm going to stop here for today. So if there are no questions, that's basically it. And let me see here. Let me get my grade book so I can take roll. I'll be right back. Okay. Okay, so today is the 29th. Okay, so let me do this, do that. Stop share. Okay, so let me see here. Arius Rios is not here. Barber
Here.
is here. Excuse me. Cannon, not here. Chang, not here. Chavis, I don't see Chavis. Clark is here. DeGraff is not here. Franklin is not here. Han, not here. Panic, not here. Heron is here. Holland is here. Jurgensen is not here. Is not here. Rouse is
I'm
here.
here.
Ronald is here. Santiago is here. And Smith is not here. Okay. All right. So that's basically it for today. Any questions in the remaining 2 minutes that we have here? Any questions? No questions? Okay. Well,
All right. Take care.
yeah, that's it for today. So I see you guys on Tuesday. All right. All right.
All right.
Have a nice day.
Have a nice day. Enjoy.